Hi, everybody, and welcome. We'll get started in just a couple minutes. Hey, Lena, Rabeeh, do you hear me okay?
Yeah.
Great. Are you still seeing me, by the way?
Yes.
Great. Yeah. How's the weather in Tel Aviv, Rabeeh?
It's really cool right now. It's about 22 degrees.
Centigrade.
It's perfect weather. Centigrade, yeah. It's a perfect weather to go out, but I prefer to be here now, inside.
Yeah, you're lucky. There's a big heat wave now in the Bay Area, so unusually enough, I think. Yeah, I'm feeling more of the summer than you guys. How about you, Lena? You're located in Germany.
Yeah, but it's like 30 degrees. It's just really hot, actually, right now. I'm in southern Germany. But by the way, I love Tel Aviv. I think it's amazing. I was there already a few years ago, but I think it was really cool. It was one of my favorite business trips, actually.
Oh, great. You're lucky. Yeah.
You can come and visit us again. We welcome you back.
Yeah, I've been waiting to visit back home too. I met so many friends back in Israel. You know, the past year, we've all been just stuck in our respective locations. So, yeah, it's nice that things are starting to open up a bit.
Yeah, I heard Israel has an incidence of 1 per 100K. That's pretty good. So, yeah, I think there's a big difference to Great Britain, right? Because their numbers are rising, but they have less vaccinated people, also another vaccine. And also I heard that Israel is looking more carefully at the borders to prevent the variants to spread.
Yeah, I think they're trying to control it pretty tightly there. Yeah, here in California, the situation is pretty calm. Just, you know, crossing our fingers that it continues that way. But yeah, so far the numbers are even out here are way down, and yeah, the atmosphere is really that things are reopening. How's it on your side, Lena, in Germany?
The pandemic situation?
Yes.
In general, yeah, it's. I mean, I'm vaccinated, so for me it's good now because I can do a lot. But with 2 kids who are not vaccinated, it's then again a little bit of a restriction. But in general, the atmosphere is quite relaxed now. So let's see what the Delta variant will do to Germany.
You still need to go out with masks on.
Yeah, not outside, but within buildings, yes. Unless you are in a restaurant, then when you sit, then you can get rid of the mask.
Yeah.
So
yeah,
sorry.
In last Monday, we had a great party in our hospital. It was regarding getting rid of the masks also indoors. So now there is no need for masks also indoors.
Ah, cool.
Yeah, normal again.
Yeah, I envy you a little bit, but soon, hopefully.
Yeah, it's good that at least this sort of develops an appreciation just for everything we took for granted in the past, right? Just seeing people's faces, suddenly you appreciate it so much.
Yeah, that's true. But at least I think it will be more easy to do something like Zoom webinars or something. People get so accustomed now that they. Yeah.
Exactly. Yeah, I mean, this is a webinar is called Virtual Meetup because it started out as an in-person meetup in the Bay Area. It was in Cupertino, and it was local people gathering. Usually there are many tens of people attending, but on the downside, we were limited to local speakers or to people to be in town in Stanford or whatever. And now, this going virtual has really opened up a lot of opportunities, such as bringing you in here. So I think we're going to keep this one virtual. Okay, so not to bore our audience too much with our chit chat, I think we can get started. Welcome everybody again. My name is Moshe Safran. I head up RSIP Vision of USA, and Rabeeh Faris is the lead radiologist of RSIP Vision. And today our guest speaker will be Professor Dr. Lena Maier-Hein of the German Cancer Research Center. She's going to talk about the topic of does machine learning-based biomedical image analysis require domain experts? Specifically, how we can deal with uncertainty in medical data. What are the right ways to develop the proper validation metrics for AI in medical imaging, and just show us how really all these medical image analysis tasks do require domain experts, and how those can best be used, even though we think we're in the age of AI and of machine learning and everything's automated and you just throw the data in and train it. It's really not the case in the real world. So we're quite eager to hear of Professor Maier-Hein's experience and specific research in this area. Before we get started, just a few words about us. We're RSIP Vision. We're a 60+ person AI and computer vision solutions company for medical devices and applications. Our company is focused on creating algorithmic solutions and software for medical, mainly for surgical planning and interventional use cases. We've been over 25 years in the field, and we have software modules that are integrated and baked into medical devices that have been used to treat thousands of patients and to plan many surgeries and other medical procedures. Here's one example of how we come across these dilemmas and these topics in our day-to-day work. So this is an example from our point-of-care ultrasound module. So we're segmenting the left ventricle here in TE ultrasound. This is trained on a very specific sort of custom data set of that numbers in the hundreds, not in the thousands. So it's quite a challenge to get this segmentation up to clinical grade, into the accuracy that was needed to actually put this into the client's device and take it to the regulatory process. And how do you validate this kind of algorithm, right? So we're segmenting the left ventricle. We can see it visually, but even if you ask 3 experienced echo specialists to annotate this, you're going to get some variability between the ground truth that's given by those experts. So in the second column here, you can see in these 3 examples, the red pixels are those that were marked as belonging to the ventricle by 3 out of 3 echo specialists. The yellow pixels were marked by 2 out of 3, and the blue were marked only by 1 out of 3. And in this case, we're comparing our algorithm results, which are here on the right, just to the majority vote. So basically something that's equivalent to the yellow region. But this type of dealing with ground truth and analysis of the test set also gives us a way to quantify the variability or the inherent variability in sort of the definition of what we're looking for. And then we can quantify how well the network's output is performing, in this case, relative to the majority vote. There are many other methods and ways of analyzing this, and I think some of the research we'll see today from Professor Maier-Hein's side will also deal with similar questions. Rabeeh, any comments on this, or just in general on your role in our company before we get to the main event?
Yeah, so I think there are no 2 radiologists that can agree fully that I can tell you that. So there always will be some standard deviation. As long as this standard deviation will be in the limits of an acceptable error, then it's okay. It has no major clinical impact. So these small errors or disagreements are acceptable clinically. That's on this topic. So I will speak a little bit about my role in the company on the next slide. So as a radiologist, I think first of all, I think the answer to the questions, to the question of the topic of this webinar is yes. Does machine learning-based biomedical image analysis require domain experts? I think the answer is yes. As a clinical radiologist and a consultant for RSIP Vision, I occupy a special and unique position by being a bridge between the clinical requirements and the field needs and the technological solutions in the company. I have a wide point of view over the different parts of the medical field spectrum, which gives me a perspective on the challenges that clinicians face in their daily practice. So in our company, I am engaged in all departments and steps in a given project. For example, I guide the annotation team and perform some quality check and annotate complex cases in order to reach a ground truth. I evaluate new data and check if it's suitable for our for the solution with a certain project. I participate in the brainstorming meetings with an R&D team. And also I'm in direct contact with the medical experts in the fields if a project requires that their expertise. For all these reasons, I think that the answer to the previous question is yes. We need domain experts to define ground truth and to check our algorithm and our automated segmentation or whatever the algorithm output is. Thank you.
Thanks, Rabeeh. Yeah, I think maybe you peeked at the abstract of the talk. Yeah, thank you very much for this, and we'll hand over the floor to Lena now, who will talk about the novel ways to quantify uncertainty in medical data, how we deal with confounders, excuse me, in our medical data, with some very interesting examples, both from real data and I think also from physical methods of generating simulated data sets. Yeah, so I will transfer the presenter privileges over to you. You got it? And yeah, let's get started.
You see my slide, my presentation mode?
Yes, yes, I see it well.
Perfect. So first of all, many thanks for inviting me here. And I will get right into the topic. So I'm actually a trained computer scientist. I already did my master's thesis back then on AI-based signal analysis, and my professor, Professor Weibel, always used to say, there's no data like more data. But you would probably agree with me that you also need the right data. And I want to start with this, for me, very irritating paper in a good way that came out recently, which was published in the context of COVID-19 diagnosis. And the authors basically found that a lot of machine learning experts worldwide started to merge data sets for COVID-19 detection. And they found that many papers actually merged an adult patient data set from COVID-19 patients with an infant data set from pneumonia, which essentially means that to get a 100% accuracy, you only need to be able to differentiate children from adults. And this was one case, but it was done in many papers, and I think it's quite shocking, and it shows that you need domain expertise in machine learning-based biomedical image analysis. So why did I choose that title? I chose it because I'm a little bit annoyed because people keep on pointing to Kaggle competitions to say that now with deep learning, we no longer need domain knowledge. You just need a machine learning expert. And the proof of it is that it's the machine learning experts that often win challenges and not the people actually from the field. But my point is that once you participate in a challenge, a lot of things have already happened, from the design of the data set to the choice of the metrics, the annotations, etc., etc. So I want to talk about this today. I'm from the German Cancer Research Center, as mentioned before, and this is located in beautiful Heidelberg. Normally we have our famous bridge parties, but hopefully again this year, not sure yet. You should definitely come join here one day. And my topic really is surgical data scientist, surgical data science. So I'm basically the data scientist corresponding to a surgeon, or more generally to interventional experts. But I have also several cross topics. So today I want to talk about challenges, a cross topic in the whole field of biomedical image analysis, and also about my new ERC grant, which I received from the European Union, simply because I'm so excited about it and I really like the topic. So I picked these topics, but all of this I will frame in the context of do we actually need domain expertise. So let's start with the data set. Many thanks to all the people involved. I'm a big fan of teamwork and involving experts in a transdisciplinary setting. So I will not be able to always mention all the names, but I will show you the pictures of all the key contributors, the clinical experts that I work with, the technical collaborators, and also the contributors from my team for this first part. And I would want to give you some context from my work, but a lot of the things that I say will generalize to other topics. So just regard this as a framing. So this is what a surgeon sees, and you would probably agree with me that it isn't much. So it's very hard to differentiate the organs, to see critical structures, because this is really what you want to see. And I guess if you would ask people in the field how to approach this problem, most people would say data fusion. So you take basically preoperative data, you fuse it with the current anatomy. So this is an approach that has been very long explored, but it has some limitations. So one is the uncertainty. So a lot of morphological changes can actually happen if you compare before and during surgery, and also you're not able to account for tissue dynamics, right? So for example, you want to be able to monitor perfusion, the tissue oxygenation. This is not something that you can get from preoperative data. And this is the reason why I'm a big fan of spectral imaging. So spectral imaging, in the most simple way, let's start with a simple way, is a generalization of general video imaging. So you know that the eye is sensitive to RGB, red, green, blue, and this is how common chips are designed. But of course, if we do digital image processing, there's no need to focus on what humans can perceive. You can generalize this. You can go to more bands, more images basically that are no longer human interpretable, and even to the non-visible range of light. So why would you do that? For many reasons. So what you see here is basically the main absorbers, the main molecules that absorb light in tissue. And you also see with these characteristic curves basically that the absorbance depends also on the wavelength of light. So now if you take these main absorbers and think you're in an intraoperative setting during surgery, and you can forget about melanin, but because melanin is a main molecule in the skin, because we have a log scale, you can also forget, as long as we're in the visible range, lipids. And in the end, you end up with HbO2 and Hb, which is basically hemoglobin, a main component of blood, and hemoglobin bound to oxygen. And you can easily compute the tissue oxygenation. And as you can imagine, tissue oxygenation is really, really important for many things. We know that tissue oxygenation is different in tumors compared to surrounding tissue. We know tissue oxygenation is important to do a surgery, to do a transplantation, to do an anastomosis, etc., etc. So many applications. And typically, in my past talks, I talked about actual oxygenation monitoring. So we are now in a patient study, and you see something that we call our ischemia index, computed from the multispectral data. And you see that before and after actually causing ischemia in the tissue, we have a completely different index. So we're currently investigating basically the benefit of this method in a prospective study. But today, I don't want to talk about this aspect, but I want to talk about another aspect of spectral imaging. And for this, I want to draw your attention to sepsis. I actually wasn't aware of the fact that in some countries, the mortality actually goes up to 50% when you have a sepsis. Basically, what's the German, the English word, Blutvergiftung, blood, not infection. I can't think of the word, but sepsis, I think, is probably a commonly known.
Bacteremia.
Okay. So very severe condition. So how could spectral imaging help? If I go back to this picture that I already showed you, and now we look at the non-visible part, the near-infrared part, then you see that actually water is the main absorber of light. And we know that sepsis causes variations in microcirculation and edema. So the hypothesis was that maybe we can detect sepsis very early based on the water content. So Silvia Seidlitz, my PhD student, got the data, and she got great results, classification accuracy over 97%. And I think the most natural reaction would be to submit this right to Nature, because that's what a lot of people do. But I was skeptical because it was almost too good to be true. And also I thought of this paper here, which I only came across recently, actually. So this is a paper where they investigate the detection of hip fracture. And the authors looked at confounders, potential confounders. I will come back to what this is in a second, but what you basically see here is the results in detecting fracture. That's the little golden thing here, and then all sorts of other things. Things like the scanner model, the hardware with which the data was acquired, or the body mass index. And for me, a very surprising result was, well, for me, it was not surprising that they could reconstruct the confounders from the data. So I'm not surprised that you can basically classify the scanner model with very high accuracy. But I was very surprised about this result here, where they showed that, yes, I mean, when they did an initial study, so cross-sectional study, meaning they just put everything in one pot, all the hip fractures that they can get, and then they got an okay area under the curve. I can't remember the exact numbers, but I think it was between 0.8 and 0.9, so pretty good. And then they started matching the confounders until ending up in a situation where everything was matched, meaning that in each group you would have, so group meaning fracture versus no fracture, so you would have matching patients in terms of gender, body mass index, scanner model, etc., and then they were not better than chance. And I think this is something that we have to be very careful about. So we looked at our data very carefully, and we talked in the group what potential confounders that we may have. And we even found some that we didn't even think of just by looking at the data. So for example, we observed after looking at a lot of the images that the healthy volunteers tended to stretch the hand, while the patients, they couldn't stretch, they were in a severe condition, right? So you see the hand posture is very different. And then we also analyzed the date of the recordings, and we found that unfortunately, we didn't know this, the data was taken sequentially. So in theory, there could be a confounder, maybe because of changes in the hardware or because of weather conditions or something. So we came up with a whole list of confounders. We actually published this paper yesterday on arXiv, so it's very hot off the press. We came up with a lot of confounders and drew the conclusion that we cannot really draw a conclusion. We need a prospective study in which we do the matching. On the encouraging side, we looked specifically at the water that we can reconstruct in the different patient groups. And we found that basically what changes matches our prior knowledge. So again, domain knowledge being important here. So, but that's all I can tell you for now on this topic. Now, if you think this doesn't matter for your specific application, I almost doubt it, although I don't know the application, because I think there's always confounders. And I want to give you another example because this was so shocking for us. So here we differentiate tissue during surgery, and we got very characteristic spectra actually for the different organs. And then, long story short, at some point we realized that if we cut the data, we group this according to a specific date, then we actually get a different picture. And then we found out that on that day, the camera provider was there and did some update to our hardware, which we didn't know about, not even to the hardware, which is I think it was just a new calibration that we didn't know about. And this completely changed our measurements. So yeah, it's very important to take care of such aspects. So what can you do? I mean, once you have the confounders, you can analyze a lot. So this is actually not about the camera confounder, but the same principle here. We wanted to know where the variance in our measurements originates from. So does the variance originate mainly from our target, which is the different organs, or from the individual from which we acquire the data? And luckily, in this case, we found that really most of the variance is basically captured or caused by the organs. And this is something that we're now leveraging for machine learning. I don't have time to go into detail, and we haven't published it. But I mean, if you're interested in the research direction, maybe look at Max Welling's paper, DIVA, it's called. So we were inspired by this. But we basically now take data that we measure and we encode it in a latent space. Z is the variable that we use for this, and we basically define subspaces in latent space, and we try to encode different information on different parts of that latent space. And this actually works. So if you look at the subspace that should encode the individual, you see that if we color code the individual, we actually have clusters. And vice versa, if we color code the organ, so this is basically shown here, then we now have a nice grouping of the organ data. So we can find a better representation in our latent space. And then, yeah, the principal approach is that we can then just leverage that part of the latent space, which is important for what we actually want to do. Yeah, so this was the data. Let's go to annotations. Again, many thanks to the key contributors from my lab and also the collaborators worldwide. And I want to talk a little bit about annotations. You already mentioned in the introduction that there's never the same result from two experts, Rabeeh. And yeah, this is also one example where 3 different experts annotated the liver. And here the difficulty arises, especially from the vena cava, because do you include it, exclude it, or half include it? You could say this is a particularly tricky example, but I will show you one example where you would normally think this is the most possible. I mean, this is a very easy case. So here, again, surgery. The task is to segment surgical instruments. So you would say, okay, this is easy because you can see where the instruments are. First decision was, what do we do with crossing instruments? And you can say, yeah, okay, let's base this on the foreground. So, right, so we cut the green in 2 because there's an overlapping instrument. So far, so good. But then what about transparent instruments? Then do you still not annotate? You know, and you start seeing it's all in the details, right? Or text overlay. We said, okay, this is we just get rid of this whole box. But then what if you have text like this? You cannot, I mean, it's impossible that you annotate all the little writing. So, you know, you basically need to know what you have to do. And this is a now new result. It's unpublished, but I find it very interesting. So we investigated this question and we asked 4 professional companies to annotate our data, and also Amazon Mechanical Turk. So you probably know that Amazon Mechanical Turk can be used for crowdsourcing. So you crowdsource your annotations. So this is a non-professional platform. And then the companies were all professional annotation companies. And we had 2 different labeling instructions, one very advanced text and one that was very picture heavy. And we had ground truth basically for the annotations, or I like to call it reference because ground truth is typically not existent, but we found a very big difference between the performance. So 0 is the worst possible value, 1 is the highest possible value, and you see the differences are radical. And the only root of this is basically the annotation instructions provided to the annotators. Yeah, the bigger picture of this is actually data sparsity, really, because I mean, we talk about annotations, we want to get more annotations, and in medicine it's not always easy. So we worked on a few concepts like crowdsourcing, also self-supervised learning. We have a new paper on meta learning, which I find actually quite interesting, accepted to MICCAI, but this is a bit out of scope for today. But if you want to have a look, we will put in archives next week, I think. But the question is, what do you do if even the experts cannot label the data? And this leads me to the topic of learning from simulations. So coming back to our multispectral data, I showed you, or I started with classification. So in classification, you can label because you have the pathology, for example. But now we're interested in regression. So we want, for each pixel, we want to determine the tissue oxygenation. So remember that for each pixel, we basically have a sequence of measurement. And here you see in this animation that when the tissue oxygenation changes, then also the spectrum changes. But now the question is, how do we go from the measurements to the value? I mean, even an expert cannot give you for each pixel the oxygenation in the tissue. It's impossible. So what we have been exploring for a while now is learning from simulations. And now in this grant, we're taking it to the next level. And I will explain this now. So the setting is we have spectral measurements. So just in the example before, this was a surface measurement, basically, like a video measurement. In a minute, I will talk about tomographic measurements, but it's always the same. We basically have a grid of pixels, and in each grid cell, we have a spectrum assigned. It's the same setting from a mathematical point of view, basically. And we want to decode this information, so we want to resolve the molecular tissue composition. And for this, we basically treat image formation and decoding as a joint framework. So let me make this a bit more concrete for you. And for this, I have to introduce the concept of photoacoustic imaging, which I'm a big fan of. So this is my institute's logo on a sponge in something like a milk bath. So what would you see if you went to a gynecologist and you acquired a 3D image? You would see a sponge and a sign, but you wouldn't see the text, right? Just like you don't see the skin color of a baby or the color of the eye. Now, imagine you illuminate the tissue with laser. Then we've already learned that depending on the wavelength of light and also depending on the molecule, this light will be absorbed. And because it's absorbed, the tissue heats up. And this all happens very rapidly due to pulse laser. So this rapid expansion then leads to the emission of an ultrasound signal due to a pressure wave. And this is what we measure. So put simply, light in, sound out. And with this, we can then actually reconstruct optical tissue properties. In this case, what is written on the sign. The technique is quite novel. So you see when you compare surface imaging, in this case, we monitor the oxygenation in the brain. We basically visualize an effect called spreading depolarization. It happens, for example, when you have a stroke. And you see that, yes, we can also measure tomographically, but you also see the resolution is still much poorer. So it's a technique in its infancies, but I think it's very promising because you can measure the properties in depth and not only on the surface. So back to the problem. What we want to do is we want to train our algorithms on the basis of simulations. So we use all our knowledge to simulate the spectral data. And then we go one step further now. We don't only use simulations to enable AI, but we also use AI to improve the simulations. So it's a joint framework, and all with the purpose of reducing the domain gap between simulations and real data. Because if there's no domain gap, then we can generate whatever we want with perfect ground truth. Okay, so let me make this concrete. This would be a simulation pipeline. So we take information on the tissue geometry, we call this anatomical. We take acoustic properties, like for example, the speed of sound in the tissue. We take optical properties, like how does the light get scattered, how does it get absorbed, etc. And then we have a simulation pipeline. So a bit more simple, this would look like this: tissue properties, the simulation of the photons, the simulation of the waves. That's the three components. And I want to focus now on the tissue properties because this is a more generic problem. So what we did is the following. This is on arXiv now, about to be submitted to a journal. So we took data from ultrasound and photoacoustics, but maybe the ultrasound is more relevant here. And we basically annotated tissue morphology. So from this we can get how the vessel topology is. Where are the vessels located? What is their size, a distribution, etc., etc. And then we trained a generative adversarial model, to generate plausible tissue geometries. So with this, we then basically got. Now I'm making a long story short, but we don't have so much time. We then got a much better performance on the downstream task, which is the classification task, compared to when using simulations that were based on literature values. You know, when we said, okay, radio should be like this, location should be in the range of X, Y, Z, etc., etc. So yeah, it's early work, but we think it's very worth exploring. Maybe before moving on to the last, I think, two topics, are there any questions so far?
Yeah, I was curious actually about, by the way, just a note to the audience, you can type in questions now or later in the talk. There's a box of the user interface you should see to be able to type them in, and then we can read them off at the end of the lecture. Yeah, I was curious about the first topic of confounders. Mm-hmm. So you showed the example of a hip fracture, right? And there were so many other parameters there that could be used to predict. Do you think in some cases, for instance, of that example, it can help us if we reformulate the task? For instance, if in hip fracture we were training the network to detect, to segment the specific location of the fracture, right? To localize it, and not only to classify. Would that sort of be convincing enough for us? Because if we would see that the network is learning to actually localize the specific fracture in the image rather than just to classify it, do you think that would be enough in that kind of case to show that we've not learned confounding factors, or is it still going to be a problem?
Yes, I mean, I think it's the right way of thinking, because I mean, whole image classification is a problem with respect to confounders, and that really already leads to the topic of explainability, right? So on Twitter, I had a little conversation with somebody who told me that they also looked into such issues, and for example, in disease detection, cables can be a problem, right? So if you have healthy control group and then a sick patient, then maybe you don't recognize, for example, COVID, but the cables because the patient is sick. And they investigated an explainable AI approach. So this goes a little bit along the lines that you suggested, and that explainable AI approach actually hinted basically at the cables, showing that this is the reason they took the decision. And similar with the COVID example, I think if with explainable AI, maybe the skull would have been wasn't the skull, but some size related features would have highlighted. So I think explainability could really help a lot, or yeah, like you say, rephrasing the problem. It depends, of course, on the specific setting.
Rabeeh, any questions from your side?
Maybe later I will ask something. Not now.
Yeah, I was also curious actually about how, if you're using the GAN in the last example there with the spectral imaging, if you're using the GAN also for image generation or just for generating those ground truth masks. But yeah, I don't want to take up too much of the time. So
yeah, I mean,
is that the plan?
You could easily use it for anything, but in our case, we wanted to ensure that the physical properties are preserved. So it's really a trick of us to disentangle basically the different components in this specific setting. But you can of course use a GAN also for more general aspects. Yeah. Okay, metrics.
Maybe I can ask something now, if it's okay. For simulations matter, you said that if the experts cannot segment or annotate the lesion or the anatomy, use simulations to overcome that issue. So I'm asking how on what ground truth do you lean on in this situation? What would be your gold standard for the ground truth?
Yeah, so in this specific case, it's basically the fact that we have a lot of prior knowledge on the individual components. So we know tissue optical properties, the scattering properties of different components, absorption properties. We know that when we have a 3D scene in which we know these properties, we can simulate light propagation quite accurately with Monte Carlo, for example. We know we can simulate camera images based on photons that arrived quite accurately. So the trick is making small components in which we can insert our prior knowledge. Yeah, and I should have mentioned it because this is why I talked about it in the first place, as the domain knowledge matters also here, because it helps you simulate the right data.
Do you do a confirmation at the end of your experiment or at the end of your simulation? Do you do a reverse confirmation for the if it was right, the simulation was right or not?
Yeah, so that's of course the tricky part.
By checking the patient or the tissue.
Yeah, that's of course the tricky part, because so how do you validate, right, that what you're doing is correct? So so there you can leverage the fact that you don't need the complete spatial information, but you can also do point-based validation, right? So for example, with a blood gas analyzer, you can extract blood and determine the properties. We also do plausibility experiments when, for example, a pig is sacrificed. We monitor values over time, and we know things about the gradient of the curve, how it should look like, and also phantom measurements, of course, where you exactly control the oxygenation in the phantom and all these things. But it's tricky.
Yeah, I think it's quite common to be able to sort of make a sparse measurement of precise ground truth, and that gives you precise validation, and then for the rest, yeah, we're left with seeing that it's plausible or validating that we work on simulations, and yeah, filling in the gaps.
Thank you.
Yeah, okay, let's move on to the next topic, which is metrics. And I think this is absolutely underestimated, because especially if you're just a machine learning expert with I mean, you don't know about the domain, then you would just fall back to the standard metrics. For example, in segmentation, everybody knows the dissimilarity coefficient. It's according to our analysis used in most challenges. Actually, it gives you a value between 0 and 1, with 0 meaning no overlap between the reference contour and the algorithm output, and 1 meaning perfect overlap. And I think, I mean, the idea is very plausible, but you really have to take care of boundary conditions. So this is an example of a very small structure, for example, and you see that a single pixel difference in the prediction of 2 competing algorithms actually has a huge impact on the metric value, right? It's a game changer, 0.5 versus 0.8. And this, I think, becomes even more relevant if you think of the uncertainty that the reference is typically generated with. So as you mentioned in the introduction, I really like this paper in this context. There's a huge variability of human or uncertainty in radiologist annotation. So you really have to account for this. And I think what is less commonly known, that there's not only uncertainty on the side of the radiologist, but also on the side actually of the machine learning algorithms. So a lot of people that are not so into the topic think that if you ignore random seeds, then machine learning algorithms are deterministic, but they are not, especially not when they run on the GPU, because then the order of the computation matters, and this can also have very huge effect basically on the validation study. So you should actually run multiple runs, same architecture, same training data, but you will get different models. Different example, classification. Here, for example, class imbalance matters. I'm making this one short, but I really like this recent paper here where they said somebody introduced a new system and they reported a sensitivity of 99%, and then the authors actually did a lot of math based on the true positives and negatives and false positive, negative, et cetera, and they found that the precision was actually 0.3.
Yeah, what are they counting? They're counting frames, and how many frames contain polyps and how many frames were normal, right?
Yeah, I mean, you cannot report sensitivity without reporting the complementary value, right? Because then you could just detect everything as positive and you have 100% sensitivity. Yeah. So a lot of problems with metrics. We published a paper on this on arXiv. We will not submit this to a journal because it will be a dynamic paper where we have a lot of illustrations also of problems. It will soon be complemented for accuracy, all the pitfalls that you have when you choose metrics for a specific problem. And it really starts picking the right task that you're actually having. So this is, I think, nicely shown in this schematic here that Annika from my group drew. So here you see, from a clinical perspective, if you detect lesions, of course, the prediction 2 is much better than prediction 1 because you have all the lesions, right? But the metric will not reflect this because it's an overlap metric. And I mean, depending on the problem, I think you should consider whether you really have a segmentation task or maybe not a detection task, and the contours maybe do not matter so much. So it really needs to be thought about carefully, and we're currently conducting a large Delphi international process to make best practice recommendations, where first we basically pick the task that you have, for example, segmentation versus detection, and then we make problem-specific recommendations for metrics.
Yeah, I was just going to ask, right, do we have any standard for this? I think this is super important to have some agree upon standards for metric selection, right? Because that dice coefficient is definitely not enough. But yeah, how do we agree to speak the same language and to be able to compare different studies and different solutions?
Exactly. Yeah, so okay, for this, I will go through this quickly, but I want to mention it briefly. So we know challenges are the state of the art to assess AI. And a lot of fame is given to the winning algorithm. And we really started our whole research on challenges with the question, is the winner really the best? And I will not go into details, large consortium involved, but I want to show you this one figure because I think it really captures the problem, all the details in the Nature Communications paper, but this one is, I think it really illustrates it well. This is a very widely cited and known challenge that takes place many times, and you see that when you play around with the design choices that you have, so with the metric, with the way you aggregate, so for example, do you first compute a rank per test case that you have, or do you first aggregate the metric values over all test cases and then you compute a rank? Do you choose the mean or the median? If you put all of this together, you end up with a completely different ranking. And then, of course, this means vice versa. You can cherry pick, right? If you publish a paper, you just play around with this, and then you pick the most favorable ranking that you can get in comparison to the competitors. But long story short, rankings are very sensitive. So we developed a toolkit actually that is also open source, which addresses these rankings. I will not explain this in detail, but in this case, basically, what you see is two rankings, the colored ones, one very stable ranking, a very clear ranking based on the raw data, and one very uncertain ranking. We try to make such differences explicit, but more in the paper. So I want to talk just the last maybe 3 minutes on one last paper that we just uploaded. It said to be uploaded here, but we uploaded it yesterday. So the question is actually, when we perform a challenge or even a validation study, what do we actually learn about the problem? And I think it's very limited actually. So we learned that there's some algorithm that is ranked 1. We know more or less the distribution of the metric values, but I mean, what do we learn about the problem? Is the problem solved? What is solved? What is not solved? Why did the winner win, etc., etc. So we just proposed this concept where, in addition, basically after running a challenge, you do a metadata annotation. So in this case, it would just be things like, is there bleeding in the image? Is there motion artifacts, etc., etc. But it depends on the application, right? What you think could be relevant, and then you do a statistical analysis. And I will skip actually, unfortunately, the method, how this works, but you can read it in the paper. And I will just show you what you see then in principle. You can then relate the image characteristics to the performance of algorithms. And it can be surprising. So for example, we found that and it retrospectively makes a lot of sense, but if an instrument is actually overexposed, meaning there's a lot of light, this is not a disadvantage, it's actually an advantage because it's bright and it can be seen easily. But people before have speculated that it's a disadvantage. And same with, for example, smoke in the image. It didn't really affect performance. If you do it, we did this on 10,000, no, not all 10,000, but thousands of images. We did this analysis, and we found that sometimes the findings did not necessarily match our prior beliefs. So I think this is can be quite useful. And the next step, and this is my last slide, basically is, why is the winner the best? And I really like this picture from this recent Nature Methods paper from my colleagues. So this shows you algorithms ranked from 1 to 100, and it shows you the things that are typically reported when you report an algorithm. So which architecture to use, for example, 3D unit. You know, do you have residual connections or not? Do you have attention mechanism or not, etc., etc. And you see, this is not the decisive factor, right? So the 3D unit was used by number 1 and number 100. So there seems to be information that is not in the papers, and that requires not only domain, also machine learning knowledge, but that requires a lot of knowledge, and that is not so easy to put in place. And I don't think that people actually hide that information. I mean, some may want to hide it, but I think others are very transparent. They even publish their source code, but they don't report it because it's not clear what is actually so relevant. So right now we're tackling this approach, and yeah, hopefully in about a year I can tell you more about this, but it's a multi-center effort.
Yeah, one of the striking things about that slide is that if I see any of those colors clustering at all, it was the blue color that reads unmodified, and that was clustering towards the high end. So the unmodified is clustering a bit to the left. So that just goes to show us sort of that it's not about the architecture, right? It's about in this case maybe the annotations were pre-given, but it's about other very specific details. Exactly. And at least on the high end, you know, between whatever 0.9 and 1. Probably those qualitative measures that you showed before. Does this work on underexposed tools? Does this work on smoke, right? All those qualitative questions are are probably much more interesting than just getting a number that's going to be strongly influenced by, you know, how that particular data set is distributed between different subtypes of cases.
Yeah. Yeah, I mean, that was basically it. Long story short, I think the reason that a lot of AI research fails in practice is that we don't validate carefully enough. And I mentioned some of the factors: confounders, metrics, rankings, what do we report, etc. And I think we have to be a bit more careful with this. And yeah, I thank you for your attention, for inviting me here, and happy to take final questions.
Thank you very much, Lena. Yes, and we very much look forward to seeing how those standards continue to develop for connecting between, you know, the question which we're all interested in the end, which is what is the clinical value of a particular algorithm and how clinically useful it is, and connecting that to really specific ways to quantify and to measure the results is just so important. And we really look forward to see how those methods and standards continue to develop. When I think we have time for maybe 1 or 2 questions from the audience. So, by the way, are you still hearing me, Lena? You good?
Yeah. Yeah.
Yeah, great. So, a question from Drasil about data augmentation. So, can simulation methods such as the one you showed, the GAN-based one, be used to augment medical data when we have less data for a classification problem? So, I think he's referring maybe to sort of filling in the gaps in those sparse data sets, right, that are sort of sampled very sparsely in the space of possible types of examples. Can we use similar methods to augment the medical data?
Mm-hmm. Yeah, I mean, so there's 2. So the theoretical answer would be, well, GANs only learn the distribution of the data that you give the GANs. Hence, you should not have a big benefit compared to using what you already have. But in practice, I think, yeah, you just fill up the gaps and you actually have a practical benefit. At least that's our experience so far.
Yeah. So you see a benefit, but it's sort of more in generating more quantity, but it doesn't really let you escape the subspace of the data that you're training the GAN to mimic.
Yeah, I mean, very not, right? Because you wanna with the GAN you wanna approximate the distribution that you actually have. So in theory, you don't get out of this, but yeah, in practice, especially in our case, you have so sparse data that at least from our experience in this setting, we have a better benefit in augmenting like this compared to standard, you know, basic augmentation approaches.
Yeah, I guess sometimes even the sort of handcrafted simulation methods could be a way to do that, right? So you can introduce tools wherever you want them to be, even if they're different from the typical poses seen in the data set, or so that's a way to sort of manually make real changes. But then, of course, there's always the challenge of making those examples look more realistic. So.
Yeah, exactly. I mean, and then it's actually out of distribution, and then you have a really added diversity to the data.
So yeah, it's good to know that our you talked about explainability before, so it's always good to know that there's still a role for our common sense or the domain expertise of the human experts, right? And that we're not handing everything over to the AI just yet. Okay. Yeah, Rabeeh, any final comments from your side?
Just want to say that it was really interesting talk. I learned a lot, and thank you. Thank you very much.
Thanks for having me.
Thank you very much, and thank you very much to the audience. Please stay tuned, and you can read our newsletter, etc. Our contact information is up here. If you'd like to drop us a line or ask any questions, feel free, and we'll see you next time in 2 months. And thank you again, Professor Maier-Hein, for your fascinating talk and for agreeing to join us and give some of your time to our event. Thank you.
Bye-bye.
Thanks.
Okay, bye-bye.